Good afternoon. Thank you very much for attending this webinar. My name is Muralidharan, and my colleague Yuki Yamamoto is here to answer questions along with me here. So what we're going to talk to you about today is a new class of alloys that Oak Ridge National Lab has been working on for a few years. And within the series of alloys, the cast alumina-forming austenitic, the cast alloys are being patented recently, and I'm going to talk to you about its properties. I'm going to introduce you to some of its properties and potential applications as we see possible. So let me just start with a brief description of the technology. What we're talking about is a new class of corrosion-resistant alloys, and these alloys are designed for high temperature use in corrosive environments. On the left, I show here a piece of material, cast alumina-forming alloy, that has been exposed to a temperature of 800 C for 5,000 hours in an air plus 10% water vapor environment. On the right-hand side is a cast iron subject to the same conditions, and you can see the difference in the surface quality after the exposure. So clearly, these alloys are able to resist the environment containing water vapor and/or sulfur. So what is the design philosophy? The design philosophy in these alloys are to form a stable alumina layer, it's an Al2O3, which is actually shown here in the alumina-forming alloys. You're seeing is an aluminum-rich scale. This is in contrast. It's actually, you can see that marked here. This is in contrast to a Chromia-forming alloy, where the Cr2O3, or the chromia, is the primary oxide layer that protects the alloy from its environment. So what is the advantages? What are the advantages of having an stable alumina forming alloy? These alloys really show lower corrosion rates, and you don't have to take my word, and we'll show you the data, and you can make a decision for yourself. Because of the lower corrosion rate, they have longer component life, and then we're able to have a longer duty cycle, and of course the high temperature capability, since alumina is much stable to much higher temperatures. So what are the kinds of components that we are targeting these alloys? Here are a few components that actually are used, for example, in the furnaces, furnace rolls. These are actually cast components that are cast into desirable. I mean, these are components that are cast into desirable shapes and then probably welded afterwards. And here are two examples as a furnace roll. We thank Duralloy for providing these pictures. And here's reformer tubes used for chemical processing. And at the other extreme, these are of course industrial environments. On the other extreme, we also have high temperature corrosive environments and exhaust manifolds. And the temperatures, as I will show you later, are a little bit lower, but they're also subject to similar water vapor and sulfur containing environments. So why suddenly do we need these alumina forming alloys? Here's a kind of a brief perspective on why we need these new alloys. Of course, the traditional cast Chromia-forming austenitic stainless steels are already in vogue, and they're widely used. And of course, in exhaust manifolds, for example, cast irons are used. But as I show you in the right, there are two major drivers for the requirements for the new alloys. One is generally increase the demand for improved energy efficiency. Here is an example of the future standards for gasoline fuel efficiency. For example, the CAFA standard demands, it's 34 miles per gallon average in 2016 to a 54 mile per gallon in 2025. So this would imply that one of the methods that many auto manufacturers are adopting is just to keep more heat in the exhaust gas, which means that all the components that are subject to the exhaust gas are now subject to further increased corrosion rates. And that's driven from the automotive side. From the energy efficiency side in the industrial processes, again, there is a demand to decrease energy costs, increase productivity, and reduce downtime, which demands materials that have much better lifetime, and so that there is a due return on investment in terms of cost. So we have three broad classes of alloys that we are working on, and And these are kind of targeted at specific property requirements that we are aware of in those classes of components that we are targeting it for. And so here, I mean, I've just briefly summarized this in this table here. We have carbide-strengthened cast alumina-forming alloys that are primarily top off at about 800 to 850 C in terms of temperature of applications. These are covered by US patent, shown here, issued US patents. And the form we think that these will be used in is a centrifugal cast tubes. Of course, these are furnace hardware, furnace rolls, and of course, traditionally they are dominated by the Chromia-forming cast austenitic stainless steels. And the second class of alloys that we have are relatively higher in strength than the HK and the HP type of alloys. They have much better, much higher strength, and they have a much sharper drop-off in strength above these temperatures. So there's a hard limit as to temperature, maybe about 900 C. It's probably the maximum that you would be able to use these alloys. We have a US patent pending application on these. Again, it could be used in centrifugal cast tubes and or shaped components. What we anticipate is these would be used in exhaust manifolds and other hardware that would operate in exhaust streams, but at relatively lower temperatures in the 800 to 900 C range. And we could foresee them replacing cast irons, high CMO cast iron, for example. The D5S, which is a high nickel version of cast, it's a cast austenitic steel, but it's a cast iron. And of course, many manufacturers are even going towards cast austenitic stainless steels or even rod forms, simply to withstand the higher temperatures and corrosive environments. The third class of alloys that we really are aiming towards the ethylene cracking and radial burner tube applications, which is the temperatures are approaching about 1100 C, and where we are still, we have found that, as I will show you later, that we have identified some alloy compositions within the granted US patent application, the granted US patent, that would be able to perform at these temperatures. And these again would be pitted against the Chromia-forming cast austenitic stainless steel such as HK and HP and HN and so on. So what led to this patent application is, I just show you very quickly some of the lab scale experiments that we have done that led to this patent application. Here is an example of the laboratory scale tests done, oxidation tests done on early versions or actually versions of lab scale versions of the cast AFA alloys. And you can see that on the y-axis what you're looking at is the oxidation mass change normalized with the surface area, that is how much milligram per centimeter squared, as a function of 100-hour exposure cycles. And this is the total life. This is like 5,000 hours. And you can tell that the AFA alloys retain a very low mass change, whereas the HK and the HP alloys, for example, start shedding a lot of the oxide, and there's significant mass loss. On the creep side, again, these are experiments done at 750 C at 100 megapascals, and you can see that the HK alloy lifetime would be somewhere here, a couple of 100 hours perhaps, and we have lifetimes going up to 10,000 hours under similar conditions. So the alloys not only have good oxidation resistance, but also have good creep resistance, as outlined here. So based upon these alloys, we worked with Duralloy, who were able to centrifugally cast two alloy compositions that we down selected. And they are all about 45 to 50 iron, about 14 chromium, maybe the 25 to 35 nickel, and of course about 2.5 to 2.7 to 3.5 aluminum, some niobium 1 to 2.5, about 1 to 3. And titanium in the DAFA 30 is, you remember that the primary strengthening phase in the DAFA 30 is the gamma prime, whereas the primary strengthening phase in the carbide in the CAFA 7 is the carbide phase. And so that really is reflected in the fact that we have more titanium and more niobium in the DAFA 30, and of course similar levels of aluminum. So what have we done with what I'm going to show you here is a brief synopsis of some of these results, but we have completed tests on the thermal physical properties, thermal expansion coefficients, thermal conductivity and so on. We have tensile properties ranging up from room temperature up to 950. We have oxidation resistance up to 900, and as I'll show you in some cases up to 1100 C. And we are in the process of collecting the creep resistance data in air. We have targeted up to a maximum lifetime of about 10,000 hours rupture time. So the first set of data you see here is the oxidation resistance as a function of temperature in the environment the 10% water air, 10% water vapor environment. And what we compare here is the mass change, and there are several alloys here, and let me just walk you through these alloys. For example, the CAFA 7 is an alumina-former, and the CAFA 7 and DAFA 30 are alumina-formers, and alloy 224 is a high nickel alumina-forming alloy. And as you can tell, these alloys keep a very low mass change as a function of time when compared to the HK and the HP alloys that really have lost significantly, has shown significant loss in mass, which is related to the spalling. On the right hand side, you're seeing the 800C data, where it's just these effects are magnified. Now, as you can tell, that the DAFA 30, which is the gamma prime strengthened alloy, performs better than the other alloys, probably performs the best within this time scale. And with CAFA 7 and the alumina-forming nickel-based alloys keeping very close track of each other. So really what we have what this already demonstrates is the potential offered by the alumina-former in terms of providing good oxidation resistance. Now going up to 900 C, we show data in dry air that is devoid of water vapor. Now you start seeing some more differentiation. The grade HP alloy, as you can see here, performs the worst amongst these group of alloys. Again, the CAFA 7 and the DAFA 30, the alumina-forming alloys developed by Oak Ridge do good, and probably the best to target for is the alloy 224 under these circumstances, under these conditions. What we also show here is a lab scale version of one of our alloys within the patent that starts to almost track the high nickel alloy. And this we call the HD CAFA 4, and this is the alloy that really holds a lot of promise for the higher temperature applications. And I'll show you at 1100 C, this even is better exemplified. What we are showing here is the oxidation mass change as a function of, again, the time at 1100 C. And the nickel aluminides actually don't do as good as the alloy 224, which is, again, I just want to show you that it's got about 48 nickel and 3.8 aluminum and some iron and chromium, which is actually a nickel-based wrought alumina-forming alloy. And the HD CAFA 4, which is an ORNL cast aluminum alloy, which is also alumina-former. And you can see how these two are tracking each other very well up to about 1,000 hours. And what is actually shown here is an alloy 230, which is also a high nickel alloy, but it is a Chromia-former. So clearly, again, the alumina-forming alloys come up on top with the good performance of the HD CAFA 4 at temperatures up to 1100 C. So clearly, we have shown you the data that illustrates the potential for oxidation resistance in these groups of alloys. And the following, I'm just going to quickly run through some of the mechanical property data we have. What I'm showing you here is the modulus, elastic modulus, as a function of temperature for these two alloys, CAFA 7 and DAFA 30. And you can see that the HK alloy is actually slightly has a lower modulus, and if you're familiar with that from the data book, it seems the HN and the HP actually even are much lower than these alloys. So if you are targeting applications that would traditionally use HK, this would be a good drop-in substitute for some of these alloys, but with the advantage of improved oxidation resistance. So in terms of the strength, here's the strength of here's data showing the strength of these alloys at 3 different temperatures. As you can see, the DAFA 30 is really aimed at is a very, very high strength alloy, and is at least about double the yield strength of the other austenitic stainless steels that we show here. CAFA 7 does well, and it's at least comparable, maybe slightly lower at room temperature than HK, but definitely better than the HN and the HP. As you bump up in temperature, of course, all the strength levels drop. The highest here is 60 KSI, for example. Excuse me. And you can still see that the CAFA 7 is starting to assert itself again, and the DAFA 30 definitely has much better strength properties at 800 C. And going up to 950 C, the CAFA 7 really starts to hold its own. And this illustrates, and as you can see, the DAFA 30 is now significantly dropped in strength. And this is directly related to the fact that the strengthening precipitate is disappearing at these higher temperatures. So in terms of strength, in the DAFA 30, we are limited to temperatures about 900 or so, which is also consistent with this oxidation performance. So we have also accumulating creep data. We are still in the process of having more tests added to this as we speak. But what we show here is the Larsen-Miller plot for DAFA 30, and also superposed on that is the HN and the HK data. And you can see that the DAFA 30 performs comparable or better than the HK. Temperatures up to about 800 C. Again, remember that the temperatures above 800, 900, close to 900, the strength is going to drop off pretty rapidly. The CAFA 7, with the tests running between about 650 to 950 C so far. Here is the Larsen-Miller plot, and this data point that's shown with an arrow is an ongoing test with an anticipated lifetime of about 10,000 hours. But as you can see, that it is performing comparable to the HN at these temperature ranges. So here is a kind of a brief summary of where we see the advantages of these alloys. The ORNL alloys have good oxidation resistance, good creep resistance, are castable, weldable, and in terms of and they can operate up to 1100 C. And in terms of the cost, we kind of for comparison, we have a few broad sets of alloys here. The primary competition in some of these applications is the cast Chromia-forming alloys, and of course the ORNL technology wins through its improved oxidation resistance. And in terms of competing with the nickel-based alloys, as you can see on the right-hand side here, the cost is a big benefit as far as our alloys are concerned. And as I showed you in a couple of plots, the oxidation performance is comparable at the temperatures we have tested with some of the higher nickel alloys, which is very encouraging from the perspective of applications. Of course, in terms of cast iron, in the exhaust manifold, of course, we have much better oxidation resistance and creep resistance, with the castability of cast iron and the cost being the favored things for cast iron. Of course, this higher temperature operation is very limited. So we presented some of these results at the SAE meeting, and we did receive a good response showing some of the we were appreciated for the benefits of some, the cast AFA alloys as it pertains to the exhaust manifold application. And in summary, I just shown you that we have developed cast alumina-forming stainless steels, austenitic stainless steels, with good oxidation and creep resistance at temperatures up to 800, 850, pushing up to 900 in air, without 800, 850 in water vapor containing environments, and probably pushing up to 900 in air, dry air. We have alloy tubes that have been prepared successfully using centrifugal casting, and the work has also highlighted some of the advantages of alloys that can be pushed to the 1100 C, and we're really looking forward to working with industrial partners who would be willing to license it and move these alloys out to end user applications. And if you have any questions, we are available for comment right now, and if you have any questions in the future, you are welcome to contact us. With that, I thank you very much for your attention.
Thank you. We now will take questions that have been texted or emailed to us, and we'd like to thank everyone for submitting these questions. The first question we received was, how do these alloys compare in cost to HK or HN alloys?
If you look at the composition of the alloys, let me just go back to that slide. Let me go back to the slide here. The nickel contents is around 25 to 35%, which is right in the ballpark of these alloys. And so, since we have already demonstrated that they are castable, I think the cost would be comparable.
Thank you. Another question that we received during your talk is, have you experimented with weldability of these alloys?
That's a good question. I didn't have time. Let me just show you quickly. We were able to weld. Do you want to say anything? These alloys in the centrifugal, we actually prepared from these pieces were prepared from the centrifugally cast alloys, and we were able to weld using traditional processing. Thank you.
Great. One more question, and it'll probably be our final one to consider time, is what do you have planned for next steps?
So in terms of the next steps, what we're hoping to do is we're in the process of preparing a data sheet that contains all the properties of these alloys, and that would be available for public view probably within a 1 to 2 week period. And so we really would welcome you to take a look at the data and evaluate it for your application. And hopefully within that you'll find that there's a significant benefit to using these alloys for your and your customers' needs, hopefully. And we look forward to finding some potential partners who would be willing to license this technology. And in the future, we hope that the industrial partner would be willing to work with us. And a few steps in that process would be for example, we identified the HD CAFA 4, which has excellent performance of reaching up to 1100 C. So we plan to work with the industrial partner to make these alloys in a centrifugal cast form, test its properties, and then move it on to potential sales and benefit for both application-wise and marketability. Thank you.
Thank you very much. That concludes our webinar for today, and we appreciate your attendance.